you go out there and then you put in multiple fractures and produce the gas back up the wellbore. In order to get production, they pump fluid and sand down into those wells at extremely high pressure, break the formation down in the objective formation down here. They fracture it, so-called fracks, and that allows the gas to flow to the wellbore. The sand is used. It is pushed by the hydraulic pressure out into these newly formed fractures. That's called proppant, and that sand then holds, props, as they say, the fractures open, and the gas flows up the wellbore. They're not nerve gas. They're not toxic war agents or anything like that. They are relatively common things. On the other hand, you absolutely don't want these in your water supply. You absolutely don't. You want to keep this stuff out of your water. The amounts of the water that has to be used here are truly enormous, but tens of thousands of cubic meters of water for every one of these wells drilled. And with these chemicals in it is what's required for each and every well. And so, as in the case of the Barnett Shale, you have tens of thousands of wells. So it's quite a lot of water, quite a lot of chemicals, quite a lot of technical requirements. You'll hear a satellite photo taken of an area in Pennsylvania, Elk County, Pennsylvania. If you had visited this area in about the year 2000, you would have seen one road out there, a few farms, a few cabins, a couple small dirt roads. It was a rural, forested countryside. All of these various lines you see here, these little nodes like this, these bright spots, those are drill pads. All the various lines are roads like this, which have been carved to access sites for the development of these shale gas well sites. So it's been a massive development. If you were one of those people who liked it quiet and liked it rural and liked it to yourself, well, your world changed a lot. There's a lot of hype out there and a lot of misstatement about environmental consequences. But on the other hand, there are some very serious environmental issues here that have to be considered. One is water availability. It's tens of thousands of meters of water required for every one of these wells, and it requires thousands or tens of thousands of wells. So water availability has to be engineered. The operators have to find a source for that water. There's work now on being able to use, salt water, non-potable water. There's a lot of discussion, but it's an issue in any case. Surface and groundwater contamination. There's a lot of stuff in the literature, kind of a popular literature about imagining gas seeping up from the producing intervals into the groundwater, and that doesn't seem to be the case. The biggest threat, really, at least in my judgment, is things like trucks spilling. Pipelines breaking. Some idiot overturns his truck and dumps something into the creek. So it's losing control of the flow back water at the well site. There's no curing idiocy, and so it's a matter of care and regulation, safety, and it's a matter of risk. As we showed from the previous slide, landscape modification, because of the massive scale, the wide extent of these developments, whole areas in the western U.S., for example, that used to be sort of the backdrop for Western movies, the wide open spaces, they now look like industrial complexes. I mean, it's just wells and roads and pipelines, and oh my God. So the landscape changes, and so things like wildlife habitat, like migration corridors, like fisheries, like air quality. There's dust, there's fumes. There's a lot of traffic and noise. There's a lot of environmental impact, and finally, induced non-native species being injured. A lot of things go on, and finally, induced seismicity. There's been a lot of press about this. There's very little doubt that under some circumstances, when you inject fluids deep into the subsurface onto fractures or faults that are sitting near failure, you reduce the friction coefficient on that surface. That makes it more likely that an earthquake can happen. There are, as I understand, a few cases where small earthquakes can be tied to these hydrofracks. More often, the documented cases of induced earthquakes are from disposal wells. So where they're disposing toxic waste from chemical weapons factories, or perhaps disposal of flowback water from some of these shale gas wells. But it is an issue, and where it happens and when it happens and if it happens, the local population gets very unhappy. So people have to know that there is that there's an issue there. So things like disposal of unwanted fluids can be engineered. You can choose where to put that. So there are some things that can be done. You can care about where you're doing seismicity. So anyway, there are a number of very serious environmental issues here. In conclusion, these unconventional resources really are different from conventional resources. They only work, they only exist because of the systematic application of advanced technology. They cover huge areas. They require enormous numbers of wells at very high cost. There's no getting around it. You can't fix that. They're crummy resources that you have to get at by very hard work and very careful engineering.
I'm quite sure that
the U.S. and the Marcellus been published in PNAS recently. Can you comment on that? But also, I think a second issue is fugitive emissions from these wells of methane, which is an intense greenhouse gas, and that there have been recent studies also that show that it's offsetting kind of the lack of coal burning that has the same greenhouse gas potential as coal.
Yeah, I get that. I haven't done any of the calculations on that, but I understand that, and I think the question of how much leakage is associated with pipelines and wells, I mean, that's a fair question, and I think
7%.
I don't know what the answer is, but it would seem to me that would certainly be something that ought to be measured by the way of baseline and related to development for sure.
I'm Henrik, and I work for Total, E&P Denmark. And today I'm going to tell you what our current plans are for the exploration program in northern Jutland, and also for the other license we have in Denmark in northern Zealand. It was said in the beginning that we would hear presentations today with emphasis on geology. So I want to start with saying that my presentation will be the exception. I only had skills to study engineering, so you have to bear with me. That's why we asked Niels to present these few slides we had on the geology. So in Denmark, we have two licenses that we got in 2010. And we got them in a joint venture with the Danish North Sea Fund. We are the operator with 80% equity, and they have 20% equity in the joint venture. We got the two licenses through what is called the open door licensing system, where we can basically ask for licenses, send in an application to the Ministry of Climate and Energy from any time from January to September. And then we got these two licenses. One covers all the parts of Zealand north of Roskilde, with the exception of Greater Copenhagen. The other part is well, I'll be happy to hear that.
No.
No. The other part is an area of approximately 3,000 square kilometers in the northern part of Jutland. Why these two specific areas? Well, it's not very clear from the other map, but in these areas we expect to find this alum shale formation, which Niels talked about, which in fact covers an area which also includes Bornholm, Skåne in Sweden, and the northern part of Poland. We are in a situation today, by 2012, where we have found that for northern Jutland, because of an extensive work done by Dong in the mid-80s, we have a lot of seismic information, which has led us to the conclusion that we are at a point now where we are ready to drill a first exploration well, which of course doesn't mean that we have any guarantee whatsoever to find gas, and that covers the northern Jutland license. For the other license, the northern Zealand, there's basically no existing seismic data. So there we have committed for the next phase to do a seismic survey, which has to be completed by 2014. So only by then we will decide whether we will go continue that license by drilling a well, which will obviously also depend on the result we get from the Northern Jutland license. By mid-2016, if we do a discovery, at that time we have to declare the discovery commercial, and then we can apply for a production license, which will normally run for 30 years. The main driver of these licenses, of course, apart from the academic interest in investigating whether there's gas in the Danish shale, is that Denmark is at a situation now where we will run out of self-sufficiency of natural gas from the North Sea, expectedly from around 2024. So in fact, at that point in time, we will be in a situation where we have to import gas. At the moment, we are exporting approximately 30% of the gas we produce, but by 2024, we will have to import the gas. So we have a driver in being self-sufficient, and that's of course also one of the drivers for the Danish state to ask us for doing this exploration. As we all know, Denmark has a very long-term desire and goal to be completely independent of fossil fuels, but there we are talking 2050. So we still have a window of approximately 25 years to produce gas. And of course, I mean, even if Denmark is 100% on renewable sources, it wouldn't prevent us from exporting the gas. Where we are now, we are at the moment in a phase of the project where we are planning the exploration well in Northern Jutland. So we are in a period now where we are doing environmental studies. The municipality in which we're going to work, which is Frederikshavn, are doing a VVM screening, which is an environmental impact assessment of the project. They are also treating our application for installation of the drilling rig. Then what we're going to do expectedly by the end of the year is that we're going to drill one water well to do monitoring of the water quality in the area where we're going to work. And then by expectedly around mid next year, we're going to mobilize the drilling rig, and then we're going to drill, and that would take approximately 2 months to complete. So by November, expectedly next year, we should be in a situation where we have done coring of the formation, of the Elum formation, where we can decide and determine whether we have gas present in the cores of the Elum shale, yes or no. If we don't find the gas, we will plug and abandon the well, do a monitoring of approximately 6 months, and then re-establish the site. If, on the other hand, it goes like we hope, that we find the gas, we will continue with core analysis and design a production test. And then the next step will be supposedly around spring next year, 2014, so that's 2 years from now. We will start doing a hydraulic fracturing test. So in other words, we're going to do a hydraulic fracking of this vertical well that we are planning, and we are going to see what is the actual production from the well. The area that we have selected for this first well is lying on one of the seismic lines which were shot by Dong Energy in 1985. They did it as a part of a drilling of an exploration well in Sæby, which turned out to be dry, but they were targeting a sandstone reservoir. So we have rented a field, which is basically at the moment a cornfield, but it's a former sand extraction area. We can see there's sand extraction on the other side of the small road. So on that particular spot, which is located approximately 30 kilometers south of Frederikshavn, we're going to do the first exploration drilling. So as part of our permitting process and information campaign, we held a public information meeting in the town of Dybvad, which is the closest town to city, small town close to the drilling area. And we gave a presentation. We basically gave the same presentation as I'm showing you now, describing what we wanted to do, and of course many of the questions which Don brought up concerning environmental protection were of course asked and answered. So basically, as we said in the beginning, and Don explained as well, when we drill this type of well, our target is approximately 4,000 meters. That's the area that we have targeted for the coring. When we drill such a well, we do it in stages, and at every stage we do a setting of a steel casing, cementing it to the surface, and thereby isolating the areas between the actual production area or drilling hole from the environment. And this is done in stages, and we envisage to set a total of 5 casings, levels of casings cemented between the surface and the surroundings and the inner area before we go down and do the coring. And of course, setting a very heavy architecture as this is of course in the light of the fact that we might be in a situation where we have to test produce this well, do the hydraulic fracking. Therefore, it's very important to isolate the areas. As it was mentioned in the beginning, in order for shale gas wells to be economic, this shale gas has to be produced from long horizontal wells which are hydraulically fractured. And in fact, this was a technology, this fracturation in long horizontal well was a technology which was where Maersk was one of the 4 players in the early 90s, because as Don mentioned, getting oil and gas out of the Danish chalk is almost as challenging as getting gas out of shale. So what we do when we do the hydraulic fracking, we do, first of all, we have demobilized the main drilling rig, but then at that point we installed a so-called Christmas tree on the well, and then we pump water, sand to keep the fractures open, and some additives into the well under high pressure in order to create artificial fractures for the gas to flow. Then after a period of time of pumping, we stop pumping, and then we start to back produce the water back to the surface, and then if the well is successful, then the gas will push the water out of the well, and then at one point in time we can start producing the gas. But in fact it's just a test to test whether it works. The next step will be to, if this is successful, to drill a horizontal well to measure the real gas rate. We need some additives for this fracturing to work. The main reason for the need for these additives is that
it's not true.
First of all, we need to add sand or particles, ceramic particles, you can see down here, in order to keep these tiny fractures open. Because what happens is that if you just inject water and back produce the water, then the fractures will close together. So we need to add this so-called propellant or sand to the water when we inject it. In order to keep this sand in place in the formations, we need to inject with the sand a polymer. In fact, it's a guar rubber, in order to make the propellant sticking to the surface and keeping to the inside the fractures. If you're talking about a production well which has to produce for many years, then in many cases you need to inject a biocide with the water in order to avoid that you have bacteria growth in the well, and you can need, for example, a corrosion inhibitor in order to avoid that your tubing is eaten up by corrosion.
I'm sorry.
Yes.
What's a biocide? Because as I understand it, it means kill life. to kill life, right?
Yeah,
so
bacteria.
What's a biocide means killing life.
Yeah.
So what is a biocide, and what biocide are you going to use? And how can you write there that they are approved by REACH when they are not?
Well, in fact, in order to use them in Denmark, they need to be registered in REACH, and they also need to be registered in the ProBas register, which is the Danish equivalent.
What about the mixture?
Same thing. I mean, all the components has to be registered. Both.
Can you prove this to us, that it has been approved by REACH?
No, because we don't have the list yet. When we have the list, it will be sent to the Danish authorities, but that is before we inject it. We are very aware of the problems of very extensive water usage, and it's true that if we go for a commercial development in Denmark, the most logic would be to use seawater as frac fluid, because we have scarce freshwater resources, and seawater is just around the corner in every place of Denmark. We have the land use problem that it would be very difficult to imagine projects in Denmark with thousands of wells, because we simply don't have the space. Talking about the risk of groundwater contamination in relation to hydraulic fracking, one point is, of course, as we have already discussed, the issue of spills on the surface. This is the classic problem that you have a truck delivering the chemicals, which is tilting over and spilling the products into the surface. This is something that's, which is the case for basically all industries, and this is the reason why when we set up this drilling site, we will isolate the area with watertight membranes on the surface. The second problem, which is also a risk factor, is that due to poor cementation, poor isolation of the. If we don't get it right when we do the completion of the wells, then we have a risk of generating, for example, also due to corrosion, a loss of confinement between the well casing and the inner production string, and that could lead to pollution. The third factor is the factor which more applies to very shallow formation, is that some people say that in some cases, under some circumstances, if you're fracking in very shallow, for example in coal bed methane layers, which are very shallow, you have a risk of fracking directly into the aquifer levels if you imagine that your fractures will propagate and activate a system of existing fractures. We can say for the area that we are looking at fracturing in an area which is at the depth of approximately 4,000 meters. At the moment, we don't know the geology of this layer, so one of the reasons why we need to do the exploration drilling is also to investigate what is the geology. Is it a risk that we should consider that we could have methane seeping into the groundwater? Today in Europe, we don't know. We have some estimates, very high-level estimate from the International Energy Agency from 2011, which in the case of Denmark gives a potential of 23 TCF. And as a comparison, the gas we have produced from the North Sea has been 5 TCF until date. So we are potentially talking about very high potentials, but of course, I mean, today we are in an unexplored area where we don't really know. At the moment, we have several drilling activities ongoing, especially in Poland. Poland has given more than 100 licenses for this, but they are, even in Poland, which has been really at the forefront of this, has not yet come to a point where they have declared any of the shale plays for commercial. What happened in France was that there was a number of licenses given in France, even earlier than the licenses in Denmark. In France, there was a public unwillingness to look for these resources. I mean, it's not. In fact, it's not for me to speculate into the reason. The only thing I can say was that at that point in time, where the ban was put in place in France, there was no scientific justification for this ban. Of course, France is in a bit of a different situation than Denmark. For example, 80% of the French electricity comes from nuclear power. And we don't have any nuclear power plants in Denmark. Maybe it's something we should consider, but we are not in that situation today.
Hey Denmark, I'm Laura. I'm fighting against fracking in the United States, and now I'm here studying in Copenhagen, and I found out it's coming here as well. We need to say no to skifergas. Skifergas nej tak. Hydrofracking. 4 syllables, poison to hear, but what does it mean? Sounds kinda vague or unclear. How does it work, and why is it bad? Why are so many people fuming fracking mad? Hydraulic fracturing. Specifics differ depending on the type of rock, but for this unconventional, horizontal, slick water natural gas drilling, you're going to need a well. Dig and send a pipe deep down into the ground, more than 6,000 feet down, and run it horizontally for over a mile. Mix in some sand and additive chemicals and millions of gallons of water. Pump that mixture down deep, pressure cracking the shale, letting the gas flow back up and out of the well. And bam, that's a rocky gist of it for you. Well, frack is whack, and we're on the wrong track. In terms of energy, different by default does not equal better. It's great that hydrofracking doesn't rhyme with oil or coal, but that in itself doesn't mean we're achieving any real goal. Because in terms of air pollution, it's just as bad as coal. Property owners misled. Seismic activity induced, frack fluid left untreated. And that's not all. Animals are getting sick and losing their fur. And people are getting cancer. Legislators, please learn the stories of those suffering. See the families, not masses. Don't go stripping humanity's face so at the ballot you can cast your vote without disgrace, because after all, you don't have to meet the gaze of those you ostracize if you deprive them of eyes. Additives contaminating our groundwater, drinking water, water from the kitchen sink faucet catching on fire when a match is lit? I thought water was supposed to put out fire. Oops. Many places in our world don't have access to clean water. Let's not frack ours up, but rather assess this situation, not devote money towards expanding hydrofracking, spreading invisible poison to the public into the pipes of our homes. If that's not breaking and entering, then tell me what is, because it's entering our bodies and breaking them down, and the shale is sure as hell cracking. We need to be putting money towards developing clean, renewable energy. We need to ban hydrofracking. No. Frack, no. Hydrofracking has got to go. I said no. Say no. Hydrofracking has got to go. I heard this once, and I'll say it again. This movement isn't just about climate. It's about liberation. Freedom to breathe clean air and water to drink. Frack y'all. Tell me what the Lorax would think.